Have you ever driven across a massive bridge and wondered, how does this thing stay standing for decades, even centuries? What keeps it from crumbling under thousands of vehicles, extreme weather, and even earthquakes? The answer lies in a brilliant blend of science, engineering, and innovation that stretches back thousands of years. Today on Structures of Scale, we're diving deep into the world of bridges, from ancient Roman aqueducts to modern megastructures like the Millau Viaduct and the Akashi Kaikyo Bridge. We'll uncover the principles, materials, and engineering decisions that allow these structures to defy gravity and time itself. Let's start by understanding the fundamental forces acting on a bridge. Every bridge, no matter its size or style, must battle gravity, compression, tension, torsion, and shear. Gravity wants to pull the bridge down. Vehicles, people, wind, and even thermal expansion all contribute to dynamic loads that fluctuate constantly. A successful bridge must not only carry this weight, it must manage it strategically across its entire form. Engineers use different structural types depending on the environment, length of the span, and the loads expected. The most common are beam, arch, suspension, and cable-stayed bridges. Beam bridges are the simplest, using horizontal beams supported at both ends. Think of them as giant planks. They work well for short distances, but become inefficient as spans grow longer. The beams experience bending, compression on the top, and tension on the bottom. Arch bridges, on the other hand, use curved shapes to transfer loads outward and downward into abutments. The Romans used this concept to build aqueducts and stone bridges that still stand today. Why? Because the arch is a naturally strong structure. It disperses the force of gravity efficiently, which makes it ideal for materials like stone and brick. Then come suspension bridges, those long, elegant spans like the Golden Gate Bridge. They use massive main cables hung between towers, with vertical suspender cables holding up the deck. The weight of the bridge and its loads are carried through the suspenders into the main cables, which then transfer the force into the anchorages at each end. This design allows suspension bridges to span incredible distances, over 2,000 meters in the case of the Akashi Kaikyo Bridge in Japan. Cable-stayed bridges might look similar, but they function differently. Here, the cables run directly from the towers to the deck in a fan or harp pattern. They're more efficient than suspension bridges for medium-length spans and use less cable overall. The Millau Viaduct in France, the tallest bridge in the world, uses this technique. But no matter the type, all bridges face the same question. How do you make something this large last for 100 years or more? Material selection plays a key role. Stone used in ancient bridges is incredibly durable and still valued for its compressive strength. But in the modern world, steel and concrete dominate. Steel is strong in tension and relatively lightweight, which makes it perfect for cables, beams, and frames. Concrete, especially reinforced concrete, resists compression and can be shaped to fit almost any design. When combined, they become a powerful duo, able to withstand both tension and compression over time. But building for durability isn't just about strength. It's also about protecting the structure from the environment. Bridges must be able to handle temperature fluctuations, salt corrosion, water, and seismic activity. For instance, in colder climates, freeze-thaw cycles can cause concrete to crack. Engineers combat this by using air-entrained concrete, which contains tiny bubbles that give expanding water somewhere to go. In coastal regions, salt spray can cause steel to corrode. To prevent this, protective coatings, galvanization, and corrosion-resistant alloys like weathering steel are used. Maintenance is critical too. Bridges are regularly inspected for fatigue cracks, rust, joint wear, and other signs of stress. Some modern bridges even use embedded sensors to detect strain and stress in real time. Seismic design has become especially important in recent decades. Engineers use flexible joints, isolation bearings, and dampers to help bridges absorb and dissipate earthquake energy without collapsing. In places like California and Japan, these systems are vital for public safety. One of the most incredible recent advances in bridge engineering is the use of modular construction. Prefabricated segments are built off-site, transported to the location, and assembled like giant Lego blocks. This reduces construction time, traffic disruption, and safety risks. The Yavuz Sultan Selim Bridge in Turkey was built using this method, spanning over 1,400 meters and combining both road and rail traffic. Let's not forget about the role of aerodynamics in modern bridge design. You might remember the famous collapse of the Tacoma Narrows Bridge in 1940. It was a suspension bridge that twisted and swayed uncontrollably in strong winds before dramatically collapsing. This disaster led to a deeper understanding of how wind interacts with large structures. Today, wind tunnel testing and aerodynamic modeling are essential steps in bridge design. Bridges are often streamlined or include open trusses to allow wind to pass through rather than resist it. But what truly separates bridges that last centuries from those that fail early? It often comes down to foresight. Great bridge engineers don't just design for current loads, they anticipate future growth. They build in redundancy, meaning the bridge can still stand if one component fails. They make maintenance easy, with accessible pathways for workers. And they ensure the materials used can be replaced or upgraded as needed. Let's look at a few examples. The Brooklyn Bridge, completed in 1883, was designed with such forward thinking that it carried trolleys, cars, and now pedestrian walkways more than 140 years later. The Forth Bridge in Scotland, completed in 1890, is a cantilever railway bridge still in use today, thanks to robust design and constant maintenance. Meanwhile, the Akashi Kaikyo Bridge was engineered to survive typhoons and earthquakes and is expected to last well over a century with proper upkeep. What about the future of bridge building? We're now exploring carbon fiber reinforced polymers, self-healing concrete, and 3D printed components. These materials offer strength, reduced weight, and even the ability to repair micro cracks on their own. AI and robotics are being used for inspection and maintenance, allowing us to detect issues before they become serious problems. And while many bridges are built for practical reasons, to connect cities, cross rivers, or span valleys, they're also powerful symbols of connection, innovation, and human ambition. Think of the Tower Bridge in London or the Sydney Harbour Bridge, iconic, beautiful, and functional. In the coming decades, as cities grow and climates change, bridge engineering will evolve too. Designs will become smarter, lighter, and more adaptive. But the core goal will remain the same: to build structures that stand the test of time, physically, functionally, and even culturally. So next time you drive across a bridge, don't just admire the view. Think about the hidden calculations, the invisible forces, and the remarkable engineering keeping you suspended in the air, safe, stable, and moving forward. If you found this deep dive into bridge engineering fascinating, don't forget to subscribe to Structures of Scale for more videos just like this. Like this video if you learned something new, and drop a comment below to tell us your favorite bridge in the world or a topic you'd love us to cover next. Thanks for watching.